Welcome to lesson 4, and today we're going to be talking about series. By the end of the day, we're going to be able to define the word series. In particular, what is the difference between the word series and the word sequence, which I know I personally will accidentally get those mixed up all the time. Define the words geometric series and telescoping series. Informally define convergence and divergence for a series. And then for those two different types of series, geometric and telescoping, we want to be able to determine when they converge, and if so, what's the value of the series. A series is a sum. But not just any sum. A series is a sum of all the terms in a sequence. For example, suppose that I have the sequence where a sub k, I'm going to switch to using the index of k rather than n, can be obtained by taking 1 over k with the first term a sub 1. Then the associated series, the series would be the sum of all the terms in this sequence. So 1 over 1 would be the first term in the sequence, and then I would add 1 over 2, I would add 1/3, add 1/4, and add 1/5, and so on and so forth, all the way to infinity. I would keep tacking on these progressively smaller fractions. I would just keep adding them together ad infinitum. In other words, a series is an infinite sum. A sum of infinitely many terms, the terms in a sequence. Now, because a series is a sum, we can represent a series using the same notation that you used for sums back in Calculus 2, when you did so-called Riemann sums for functions. So we can use this sigma, Greek letter S, S for sum. Below we have the index, I'm just going to use the letter K for short. And then below the sigma we indicate the starting number. Above that, where we would normally have the number where the sum stops, the final number for the sum, we're going to put infinity, because a series is an infinite sum, adding together infinitely many terms of a sequence such as a sub k. For example, if I wanted to use sigma notation to represent the series above, I would sum from the starting index of k equals 1 up to infinity, the sequence whose formula is given by 1 over k. That would be sigma notation for the series at the top of the page here. So what are series used for? What is their purpose? What's their point? A series is used to take a number that is potentially complicated and difficult to work with, a number such as something containing pi or e or the square root of something, to take that and break it down as a sum of simpler numbers. Breaks down a complicated quantity, something that might be difficult to work with, as a sum of simpler quantities. For example, we have below some historical approximations for the values of the number pi, and this comes from the 17th and 18th century. Back when people were walking around and they did not have calculators in their pockets. If they wanted to do a real-world application with a number like pi, they couldn't exactly go out to MATLAB and plug pi into their program. They needed to do the calculations either by hand or with a really simple tool such as an abacus. At that point, it became necessary to have convenient representations of the number pi. And so, for various purposes, various representations of pi were developed. For example, one way to obtain pi is to take the number 4 and multiply it by the following series. Take the number 1 and add minus 1/3, then add positive 1/5, add negative 1/7, and so on and so forth. The signs alternate, and the denominators are steadily increasing odd numbers. Another way, one of the more famous and elegant formulas does involve pi squared rather than pi itself. But this one's quite miraculous, that if you take pi and square it and divide it by 6, that number is somehow the same as what you would get if you took 1 over 1 squared, added 1 over 2 squared, added 1 over 3 squared, and so on and so forth. This is equal to the series, which you can get by summing from 1 to infinity 1 over k squared. That's equal to pi squared over 6. So this is quite a beautiful representation of pi squared over 6. So if you only wanted maybe an approximation of pi to 4 or 5 decimal places, then one option would be to perhaps just take the first couple of terms in this sequence, add them together, and that would be approximately equal to pi squared over 6. So you could calculate this sum by hand, you could multiply that result by 6, and then you could take the square root of that number, and you'd have a pretty good approximation for pi. Functions can also be broken down as a sum of simpler functions. The Taylor series, in particular, aims to represent a function f of x as a sum of power functions, which power functions, you might recall, means a function which is just some number times x to some power. This is really, really useful, for example, if you want to take the derivative of f of x, because you can take the derivative of a sum really easily using the sum rule, and you can take the derivative of power functions really easily using the power rule. So this provides you with a really, really easy way to take the derivative of a complicated function. We will actually be covering Taylor series later in this chapter. Finally, Fourier series. Now, we will not be covering Fourier series in this class, but you're likely to encounter these series if you go on to be a math major. Probably if you end up being a sound engineer of some sort, and almost certainly if you become an electrical engineer. Because Fourier series have to do with waves, and anything that can be represented as a wave. The idea in this case, Taylor series broke a function down as a sum of power functions. A Fourier series breaks a function down as a sum of sine functions. So this is useful, for example, to represent a sound wave as a combination of sound waves corresponding to really simple different frequencies. For example, the sound that comes out of a guitar or out of a human mouth is a combination of hundreds of thousands of different simple sound waves at different frequencies. It creates this noise that we understand as language or music. So Fourier series are used to represent things like that mathematically. Now, when I was first getting started learning about series, the thing that always seemed really surreal to me was, how is it humanly possible? How is it even technologically possible to add together an infinite collection of numbers? I mean, I as a human would probably add together the first 100 terms, get tired, and then go play Halo. And if we test the computer to add together an infinite collection of numbers, then it might run for a couple of hours. It might add together 10 to the 70 terms in that sequence, but eventually you're going to realize that the loop will never terminate, and so you're going to have to force shut down the program. adding together an infinite collection of numbers is guaranteed to take an infinite amount of time. So the question is, how is it possible to calculate the value of, for example, one of the series representations of pi that we had on the previous page? And the answer basically any time we're working with infinity, is to use limits. The idea is to take what are called partial sums. Take a finite sum where you add only the first n terms of the sequence. Try and find a formula for that, and then see what happens when you take the limit as n goes to infinity. Because finite sums are something that can be calculated by hand, limits are something that can be calculated by hand. When you put them together, you get an infinite sum that can be calculated by hand. Which brings us to our definition for today. A series converges if the limit of the partial sums, which are usually represented as sub n, which are obtained by adding together the first n terms of the sequence. The limit of the partial sums exists. In other words, as you keep adding on more and more terms, these finite sums begin to converge on to approach some fixed finite number, so that as n goes to infinity, and you're ultimately adding up infinitely many terms, the result of that sum is some fixed finite number. And so in that case, we say that the series value is equal to that limit. If you want to add up a collection of infinitely many things, start by adding up a collection of finitely many things. And then let the number of things that you added up grow to infinity in a limit. That number is equal to the so-called value of the series. Now, if the series does not converge, of course our usual term for that is that the series diverges. Let's test out this definition in the following example. Let's determine whether or not each of the following series converges or diverges, and let's just give an informal argument. So we have the series where we're summing from k equals 1 to infinity the terms of the arithmetic sequence where we have a common difference of 2 and an initial value of 1. So, let's calculate the first partial sum, where we're just adding as k goes from 1 up to 1. Now if I plug k equals 1 into this formula, I get 2 times 1 plus 1, so that's just 3. So that's the value of our first partial sum. What about the second partial sum? Now we're adding up the terms from the first to the second. So when k is equal to 1, we get 3. When k is equal to 2, we get 2 times 2 plus 1. So now we're going to add 5. Result 8. When n is equal to 3, then we'll take the partial sum up to 3. 2 times k plus 1. Then I have 3 from k equals 1, 5 from k equals 2, and finally I also have 7 from k equals 3. So that's equal to 15. And then we can confirm that s sub 4 is equal to 15 plus 9, so that's 24. And s sub 5 is equal to 24 plus the next odd number, 11, 35, and so on. Let's look at the result of the partial sums. We have 3, 8, 15, 24, 35. As n increases and we keep tacking on more and more terms of the sequence, the value of the partial sums is growing toward positive infinity very, very quickly. So when we take the limit, the value of the sum is just going to get closer and closer to positive infinity. So the limit is equal to positive infinity, and the series does not have the value of a finite number, so the series diverges. Let's consider what we would get, if we get anything at all, by adding up the terms in the sequence -1 to the k, starting from k equals 0. So if I take S0, we're summing from 0 to 0, -1 to the k. When k is equal to 0, we get +1, and then we stop. S1 is the sum from 0 to 1 of -1 to the k. So I get 1 from k equals 0, then I get -1, so the result is 0. If I calculate the sum up to n equals 2, then I'll get the 0 from before, plus when k is 2, I get +1, result 1. Then S3 is equal to 1 plus when k is 3, I get -1. S4 is back to being +1, S5 is equal to 0, and so on. Now notice that the terms here, the results of these partial sums, alternate between +1 and 0. Because these partial sums keep alternating, the limit as n goes to infinity of the partial sums does not exist, which means that the series diverges. And it isn't possible to get a single well-defined number by adding together alternating powers of -1. Let's consider this series. We have the sum as k goes from 1 to infinity of -1/2 to the power k. So in my spare time, I've gone ahead and I have calculated the first 5 partial sums for this particular series. When s has a subscript of 1, for example, and I'm summing as k goes from 1 to 1, then I just get 1/2 to the power 1, which is equal to 0.5. When n is equal to 2, then I get 1/2 plus 1/2 squared, which is 1/4. So the result of that is 0.75. S3 works out to be 0.875, S4 works out to be 0.9375, and S5 works out to be 0.96875. So as we add on more and more terms, it looks to me like the values in the partial sums that we get as a result are approaching 1. So this series actually does converge. And we also know, if we manage to sit down and add together every term in this infinite sequence, we would get as a result the number 1. Series converges, and the value of the series is 1. And we could also write that if you sum as k goes from 1 all the way to infinity, 1/2 to the power k, the result of that will be the number 1. Now the series that we saw in the previous example was an example of specific kind of series called a geometric series. And a geometric series is just what you get when you add together the terms in a geometric sequence. Now, for geometric series, we have a very nice theorem that we can use to know right away, very quickly, without calculating any partial sums, whether or not the series converges. Not only that, but we will have a formula for the number that the series converges to. So, theorem, convergence of geometric series. The geometric series sum as k goes from 0 to infinity of common ratio r to the power k. This series is going to diverge and it's not going to equal a number if the common ratio is greater than or equal to 1 in magnitude. So either that larger than or equal to 1 or less than or equal to -1. But if the common ratio is small in magnitude, if it's close to 0, if the common ratio is less than 1 in magnitude, the series will converge. And not only that, if it does converge, the value of the series is equal to 1 divided by 1 minus r. That's it. That is the formula that can be used to find the sequence's value if you know that the common ratio r for your series is less than 1 in absolute value. Now, pay close attention here. In this one theorem, there are 3 separate if-then statements. The first thing that this theorem is telling us is if the common ratio is large, so here's the hypothesis, then this series diverges. So this is part 1, the first thing that this theorem is saying to us. The second thing that it says is that if absolute value of r is less than 1, so a totally different hypothesis unlocks a totally different part of this theorem, which has the conclusion that if that's true, then the series converges. And the final if-then statement that's hiding in this theorem is that if you know that the series converges, if this common ratio is smaller than 1 in magnitude, then the value of the series is 1 over 1 minus r. So 3 separate hypotheses leading to 3 separate conclusions. Now I want to do a little proof. I want to explain to you why this theorem is true. And so in order to do that, the first thing that I want to do is find a formula for the partial sum that you get by adding up the terms up to the index n. So let me go ahead and write out the terms in this partial sum. When k is equal to 0, I get r to the power 0, and that's 1. Now when k is equal to 1, I get r to the power 1, and that's r. Then r squared and r cubed and so on, all the way up to r to the power n, capital N, our final term in the sequence for this particular partial sum. Now notice something. What happens if I take r, the common ratio, and multiply it by Sn? Then I'm going to get r times 1, r times r times r squared, and so on, all the way up to r to the capital N. So if I distribute that, then I get r plus r squared plus r cubed all the way up to r to the capital N plus 1. Now notice that this is almost exactly the same as my original partial sum. We have an r and we have an r. We have an r squared, we have an r squared. We have an r cubed, we have another one up here somewhere. And we have an r to the n up here. And we'll have an r to the n, the bottom sum as well. So if we subtract these two, if I take Sn and I remove r times Sn, then a lot of the terms here are going to cancel out. The r in Sn will cancel with the r in r times Sn. The r squareds will cancel when we subtract them. The r cubeds will cancel when we subtract them. The r to the n will cancel. And the only thing that will be left is the 1 from Sn on the far left side, and the r to the n plus 1 from the second series on the far right side, which we're subtracting. So let's do a little cleaning now. Let's do a little cleaning. On the left side, let's factor out Sn. That leaves 1 and r behind. And let's isolate Sn by dividing. I want to determine under what circumstances the series converges. In other words, I want to consider under what circumstances the limit as n goes to infinity of Sn actually exists. But since I've found this representation of Sn, I could consider under what circumstances does the limit of this fraction on the right-hand side exist. And that's where we get into the magnitude of the common ratio. If r in magnitude is greater than or equal to 1, then this limit will not exist. If r is larger than 1 strictly, we're going to run into a problem of the quantity r to the n plus 1 just growing limitlessly and getting larger and larger and larger. R cannot be equal to 1, because if that is true, we end up dividing by 0. That's no good. And if r is equal to minus 1, we're going to have a problem of the terms alternating between plus and minus as the exponent changes from even to odd. But if r is smaller than 1 in magnitude, then the r to the n plus 1 vanishes, because we're taking something like 1/2 or 1/4 to increasingly large powers. So limit will exist, and it will equal 1 over 1 minus r. So that is the rationale behind the theorem on convergence of geometric series. Let's determine whether or not each of the following series converges, and if the series does converge, let's find the value of the series. And let's give a formal argument. Let's use the theorem from before to convince the skeptic. Okay, so the first thing that we have is the sum as k goes from 0 to infinity of 3 to the k. So in this case, the common ratio is equal to 3, and 3 in absolute value is larger than 1. So the hypothesis of one of the three parts of that theorem is satisfied. And we can conclude by that theorem that this series must diverge. And it's as simple as that. Consider the common ratio. If it's greater than or equal to 1 in absolute value, the series must diverge as a result of that theorem. So let's consider the next series. The sum as k goes from 0 to infinity of minus 1/4 to the power k. In this case, the common ratio is negative 1/4. If I take the absolute value of that, I get positive 1/4, and that is smaller than 1. So by the theorem of the previous page, the series must converge. It converges as long as the common ratio is smaller than 1 in magnitude. What's the value? The value of the series, the number that it represents, is 1 over 1 minus r. Since our r is equal to negative 1/4, this series is equal to the number 1 over 1 minus negative 1/4. So 1 over 1 plus 1/4, 1 over 5/4, which is equal to 4/5. That is the number that is equal to the result of adding together all the terms in this geometric sequence. Now what about this one? We have the infinite sum 3 plus 2 plus 4 over 3 plus 8 over 9 plus 16 over 27. Now this is not in sigma notation, so the first thing that we're going to try and do is find a formula for the terms in the sequence. Let's consider the common ratio. If I calculate the ratio of the second term to the first term, then that's equal to 2/3. And let's just confirm that's the same thing as the ratio of the third term to the second, which is the same thing as the ratio of the fourth term to the third, which is the same as the ratio of the fifth term to the fourth. Do a little fraction arithmetic, and you can confirm that all of these ratios are equal to the same number, 2/3. Let's also acknowledge the fact that our initial term, our a0, is equal to 3 in this case. So the formula for our sequence is equal to 3, the initial value, common ratio, to the power k. And so our series is the sum from 0 to infinity of 3 2/3 to the power k. Now comparing what we have to the expression in the theorem, notice that the expression in the theorem doesn't have a visible initial value, a0. However, let's use some properties of sums to set that initial value aside. We can essentially take that initial value of 3 and factor it out. So we have 3 times the series where the common ratio is 2/3. Since the common ratio is smaller than 1 in absolute value, this series does converge, and its value is equal to 1 over 1 minus r. In our case, 1 over 1 minus 2/3. So that works out to be, I think 3 times 3, that works out to be the number 9. Let's consider the next series. In the next series, we have a sum of 1 over 7 to the power k. But what's tricky about this problem is that the starting value of this series is no longer 0. This time, instead of starting with 0, we start with 3. So compared to the kind of series that's in the theorem, our series is missing a couple of terms. We're missing 1 over 7 to the power 0, we're missing 1/7 to the power 1, and we're missing 1/7 to the power 2. Now, if we did start the sum from 0, the theorem tells us that the value of this series would be 1 over 1 minus 1/7. Or in other words, I guess it would be 7 over 6. But that's the series starting at 0. We need to calculate the value of the series if it starts at 3. What we can do to find the value of the series starting at 3 is to take this 7/6 and subtract the 3 terms that are missing. Once we subtract the 3 terms that are missing from our series, then we'll get the value of our series. So, big takeaway is be careful of starting value. As it will affect the number that your series is equal to. Now finally, as our last example of a geometric series, where we have the sum from 0, so the correct starting position, to infinity of 4 to the 2k times 5 to the negative k. Now at first, this series may not look geometric, but let's see if we can do some rewriting to make it look geometric. I'm going to use some exponent formulas here. First of all, I'm going to use the fact that 4 to the power 2k is equal to 4 squared separately to the power k. I'm also going to use the fact that 5 to the power negative k is the same as the reciprocal of 5 to the power positive k. So 16 to the k times 1 over 5 to the k. And finally, since now these both have exactly the same exponent, they can be combined. 16 over 5 to the power k. So our common ratio is 16 over 5. The series is geometric with this common ratio, which is larger than 1 in absolute value. And because of that, we know that the series diverges. The last kind of series that I would like to talk to you about today is a series called a telescoping series. Now, this is an informal definition, and it's used to refer to the fact that when you calculate a partial sum of the series, most of the numbers in the partial sum end up canceling out. I say internal numbers canceling out, imagine a situation like this. Imagine that when you go and calculate the sum, you get something like 1 minus 1/2 plus 1/2 minus 1/3 plus 1/3 minus 1/4 plus 1/4 minus 1/5. If this was equal to your partial sum, then we can see that all of these internal numbers here, everything from minus 1/2 to positive 1/4 ends up canceling, leaving us with just the term on the far left and the number on the far right. So a series like this is called telescoping because, like the old collapsible spyglasses of old, you can basically collapse this partial sum, leaving only the left end and the right end. Everything in the middle cancels something else out, and the sum collapses.
It's in its compact form, so if I pull this sucker out, ooh, look at that.
Now, when you see a series, it may not be obvious at first that the series is going to telescope. To give you an example, let's consider the series where the associated sequence is 1 over k squared plus 3k plus 2. Let's show that this series is telescoping. In other words, when we write out a couple of partial sums, we'll see that those partial sums have a lot of internal cancellation. The first thing that I'm going to do in order to reveal that fact is I'm going to use partial fractions. I'm going to take this sequence here and first of all factor the denominator, and then I'm going to use partial fraction decomposition to split it up. Now, I'm not going to, in this video, go through the process of partial fraction decomposition. This video is already gargantuan. But if you need to review this technique, you can go back and you can look at my video number 00, which does cover, in the review of Calc 1 and 2, the method of partial fraction decomposition. So looking at this, it seems like if we have a -1 and a +1, then these two things will actually be equal to each other. Okay, so having established that, let's take as an example S3. The partial sum from k goes from 0 to 3 of 1 over k squared plus 3k plus 2, except now we know that this fraction is actually the same thing as -1 over k plus 2 +1 over k plus 1. Let's write out what this partial sum would equal and let's see what happens. Now when k is equal to 0 and I plug that into this formula, I get -1 over 0 plus 2 plus 1 over 0 plus 1. When k is equal to +1, and I get -1 over 1 plus 2, +1 over 1 plus 1. When k is equal to 2, I get -1/4, +1/3. And when k is equal to 3, I get -1/5 and +1/4. Now, if we add the result of all these different terms in the sequence together, we'll get a huge amount of cancellation. The -1/2 will cancel with the +1/2, the -1/3 with the +1/3, the -1/4 with the +1/4, and the only survivors will be the +1 from the k equals 0, and the -1/5 from the k equals 3, the final term. Now, in general, if I do this analysis for S sub 4, S sub 5, and in general for S sub n, what we'll find is that all the terms except for the negative final and the +1 from the initial will cancel each other out, and so S sub n will always simplify So if I calculate the limit of that, and I let n go to infinity, then this fraction with n in the denominator will go to 0, and only positive 1 will be left. So this series converges, and the result of the series is equal to 1. For a final example of a series that is telescoping, even though it may not seem like it at first, let's consider the series where we're taking the sum of the natural log of k plus 1 over k as k goes from 1 to infinity. Once again, let's see if we can rewrite the formula for our sequence so that it might have the potential to have some cancellation. This can be rewritten as natural log of the numerator minus natural log of the denominator. So what would happen if, for example, I calculated the partial sum up to n equals 3? When k is equal to 1, the first term in the sequence, then I get natural log of 2 minus natural log of 1. When k is equal to 2, incrementing 1 up, I get natural log of 3 minus natural log of 2. And when k is equal to 3, I get natural log of 4 minus natural log of 3. So once again, because I have a minus sign attached to a term with a k, and I have a plus attached to a term with a k plus 1, these alternating signs cause these internal terms to cancel out. And all I'm left with is the natural log of 4, which came from the final term, and the natural log of 1, which came from the first term. Now if I did this process, not for necessarily n equals 3, but for n equals whatever, we would still see this cancellation. But we would be left with natural log of n as the final term, plus 1, minus natural log of 1 from k equals 1, the initial term. If I consider then the limit as n goes to infinity of Sn, which would be equal to the limit as n goes to infinity of this natural log expression, notice that natural log goes to infinity as its argument n plus 1 goes to infinity. So this series turns out not to converge because the limit of the partial sums is positive infinity. So for a series that's telescoping, the main technique is to write down a formula for the partial sum, simplify it, rewrite it, and then apply the limit as n goes to infinity. In summary, what have we done today? We introduced the word series, and we gave some examples of a series. We talked about what it meant for a series to converge and what it meant for a series to diverge. We talked about how to determine whether a geometric series converges. And if it does converge, we actually had a formula that we can use to figure out what number the series converges to. For a telescoping series, we instead wrote out a formula for the nth partial sum, simplified as much as possible, and then applied the limit as n goes to infinity. And that was our technique for determining the limit for a telescoping series. As we move forward in this chapter, we will encounter a large variety of series, and an even larger variety of techniques that can be used to analyze each of those series, determine whether or not they converge, and if they converge, find their value.